A ripple 500 million light-years wide keeps repeating. It shows up in galaxy maps from different surveys. That ripple is real structure, not a software glitch. It is the fossil ring of a cosmic sound wave. The immediate takeaway is simple: the universe leaves layered fingerprints. Picture shells in water after a stone drop. Now scale that to galaxies and dark matter. Those shells freeze in place as the universe expands. We can still measure their size today with surprising precision, and each shell hints at a deeper layer of time. We will tour those clues from light to gravity. You will see how subtle patterns build a stacked cosmos. Stay with me because these layers change how we measure everything. By the end, you will see the sky as nested history. You open a galaxy map and a preferred spacing appears. Galaxies are slightly more likely to sit 500 million light-years apart. That pattern has a name you can say fast: BAO. BAO are baryon acoustic oscillations, frozen sound waves in space. They matter because they give us a standard cosmic ruler. With a ruler, we can track expansion and test dark energy. Here is how the ruler formed in clear steps. The early universe was a hot plasma of light and matter. Pressure made sound waves race outward through that plasma. Gravity pulled back while radiation pushed out, so waves rang. When atoms formed, light escaped and the waves stopped. The stopping distance set a preferred separation in matter. Over time, gravity amplified that separation into a gentle ring. You see it today as a small bump in correlations. Example: in real terms, Sloan measured the bump near 150 megaparsecs. That is about 500 million light-years in moving terms. One sentence recap: BAO are a fossil ring that calibrates distance. Now you zoom from maps to the sky's finest grain. The cosmic microwave background looks modeled, but not randomly modeled. Those blotches line up into peaks when you plot sizes. CMB acoustic peaks are harmonics of the same primordial waves. They matter because they lock down the universe's basic recipe. With them, we measure curvature, matter, and radiation with tight error bars. Here is the working picture with no jargon traps. The hot plasma oscillated like a drumhead before atoms formed. Some spots hit maximum compression at the moment light decoupled. Others were at rarefaction, which is the opposite of compression. That snapshot fixed a pattern of hot and cold spots. When we count spot sizes, peaks rise at specific angular scales. The first peak sits near 1 degree on the sky. That maps to the same sound horizon as BAO. Planck confirmed multiple peaks, plus a damping tail from diffusion. Tiny test: if the first peak shifts, curvature changes. The net result, that peak train, shows a layered early orchestra. Take a step back and imagine a glowing shell around us. The cosmic microwave background is that shell in 3 dimensions. It is the surface of last scattering, where light went free. This shell matters because it is our earliest visible horizon. It anchors distance scales and every later layer we discuss. Here is how that shell formed in everyday language. The plasma cooled, electrons grabbed protons, and neutral atoms appeared. Photons stopped bouncing, so they began long, straight flights. That moment was not instant, so the shell has thickness. Think of a fog bank with a soft, fading edge. The thickness is tens of megaparsecs in moving distance. Slight variations across that shell seeded later structure growth. Observers map tiny temperature shifts to reconstruct early conditions. One sentence recap: the CMB is a real spherical layer. Beneath that light shell, even older messengers still flow. The cosmic neutrino background and primordial gravitational waves reach deeper. They are relic backgrounds, older layers from hotter cosmic times. They matter because they turn the universe into a layered archive. With them, we could read chapters before the light chapter. Here is how these messengers slip through the cosmos. Neutrinos decoupled about 1 second after the Big Bang. They streamed away, barely interacting, and cooled to 1.95 Kelvin. Their number density is roughly 336 per cubic centimeter. Gravitational waves decoupled almost immediately, riding spacetime itself as ripples. Radio pulsar arrays already hint at a stochastic background today. The signal sits at nanohertz frequencies, seen as correlated timing wiggles. Future space interferometers will hunt higher bands with extreme sensitivity. Example: in real terms, PTA's reported common spectrum noise in 2023. LISA aims for the millihertz band in the next decade. Bottom line, older backgrounds are deeper layers we are learning to hear. Now we hit the spicy part, the debated giant rings. Some studies claim huge concentric features in distant object catalogs. The idea is simple to say, but hard to prove. A giant ring would be a layer beyond Bow scales. It matters because it could challenge simple statistical homogeneity. If real, it would force new thinking about cosmic history. Here is what could create such a pattern or fake it. True physics could imprint shells during a sharp early transition. Survey edges could masquerade as rings in the statistics. Selection cuts can stack sources at preferred redshifts by accident. Window functions can echo, and that echo looks like structure. One published claim described a gamma-ray burst ring of giants. The quoted radius was around 1.7 billion light-years. Others saw possible periodicities near 130 megaparsecs. Many follow-ups questioned the significance with updated controls. Common mistake is treating catalog quirks as profound cosmology. What to remember: extraordinary rings need extraordinary confirmation. Switch from catalogs to spectra along narrow sightlines through space. Quasars light the path, and the intergalactic medium writes shadows. The Lyman-alpha forest is that stack of shadows by Redshift. It maps hydrogen density like contour lines across cosmic distances. This matters because it reveals sheets and filaments as layered strata. With many sightlines, you can rebuild a three-dimensional map. Here is the working picture built from photons and gas. Quasar light passes clouds, and each cloud imprints one absorption line. The line's redshift tells distance along that narrow tunnel. Many tunnels stitched together reveal a corrugated cosmic landscape. Bright regions show voids, while darker bands trace denser gas. Tomography turns thousands of lines into a textured volume. CLAMATO demonstrated this at redshift 2 to 3. Resolution reached a few megaparsecs across small pilot fields. Larger projects are scaling that technique over wide areas. One-sentence recap: the forest turns spectra into layered maps of structure. Look at the sky as stacked time shells, not flat wallpaper. A thin redshift bin is a spherical slice of history. That slice definition matters because selection effects can fool us. We can confuse evolution with distance if bins mix too wide. Here is the practical way observers handle this problem. They carve surveys into hundreds of narrow, contiguous redshift shells. Each shell tracks galaxy clustering, lensing, and motion at one epoch. Flux dims with distance, so calibrations correct brightness and color. K-corrections match observed bands to rest frame light across redshift. Volume weighting counters the changing size of shells with distance. Then they combine shells into clean time tracks of growth. Numbers in practice, DESI and Euclid will deliver dense tomographies. They will measure F sigma 8 across many redshift layers. Text overlays aside, the core idea is easy to keep. Net result: redshift slicing is how we build layered timelines. We began with a ripple that kept showing up. Now you can see how many layers stacked behind it. Bow gave us a ruler, and peaks gave a score. The CMB shell framed the stage with a glowing boundary. Older backgrounds promised deeper chapters we still want to read. Controversial rings reminded us to be careful with patterns. The forest painted strata, and redshift shells organized time. Here is the gentle ask: bring that lens to your sky. When you see a map, try to spot the layers. If this helped you see the cosmos differently, consider subscribing. Net result: layered signals turn the universe into readable history.